I'm all out. We ain't even close to rescue. How am I supposed to fight guns with a knife?
Watch your tongue. If you make it out of here alive, the government's gonna whip you straight.
But we aren't gonna make it out of here alive. This is a death sentence.
They won't take our surrender. They haven't taken prisoners through this entire war.
This is where we die. You hear that, Council? We die here because of you.
Planet Nero has fallen. This is one more world that they've taken from us. Our enemies have taken 30 of our 40 worlds since the start of the war. They're going to annihilate us within the decade. What are we gonna do?
You heard the good soldier. We need more resources. We're lacking in materials like scandium, which is essential to any high-strength material we use. We're also lacking in basic building materials like iron and aluminum.
I propose that we go onto a new planet. Our current worlds cannot sustain our productivity. Let's set up a base on a planet that contains scandium. One of my colleagues has given me a video about our options.
Let's see it.
Thank you, Councilman, for allowing me to work with you all on this immensely important project. Over the last few years, I have been studying this new planet which I have named Hart. I strongly believe Hart is Nero's last and only hope. Hart is very, very far away from the front lines of this war, making it the ideal location to start a new supply line. Now for some basic information about this planet to keep you informed about where your money is going. We will start with its star. The star on Hart's solar system is roughly 60 million miles away from this planet. It's a main sequence star in its red giant phase. My interns estimate that the red giant has roughly 250 million years before it regresses into a dwarf star. Hart is the second planet in its solar system, which has a total of 7 planets. Analysis of the absorption spectra from Hart reveals it has a CO2 and water vapor atmosphere. Hart has one moon which revolves around it regularly. Using our satellite technology, we were able to obtain a topographic map of Hart, which we will now show. Unfortunately, the pressure on Hart is enough to crush a human, with over 9 million pascals of pressure on the surface of the planet. Due to the high surface temperature, we have not yet observed any liquid water in Hart, and we're not sure if there was any to begin with. Clearly, Hart is not suited for inhabitation, so we do not believe it ever had any liquid water. But we do see faint riverbeds and some traces of ocean basins, but these may have been filled with methane at some point in the distant past. Now moving to the geology of Hart. Although we see mountains and canyons on Hart, these are all very, very old. We predict that after the formation which ceased, there are no more subduction boundaries to drive plate tectonics, the formation of new mountains, canyons, and other features driven by plate tectonics.
But do we have another option? We have to go with this plan.
We'll fund a mission to explore the planet. They can have as much money as they need, but it needs to be done quickly.
Dr. Gladstone. My name is Scott, and this is my partner Haru. We've been recently informed that we've been assigned to your unit, and what are we going to do?
Well, excellent. We'll be starting shortly. The material we'll be looking for is scandium. Scandium is what is known as a rare earth metal. The rare earths are the lengthenite series of the periodic table, plus scandium and yttrium.
Interesting, but how are we going to find these? You said they were rare, correct? It might be difficult.
They're not rare in that they're scarce. They're rare in that there is no one source of these minerals. We, however, will be looking for scandium in the mountains. The principal ore of scandium is thortwite, which is slowly cooled granite. Thortwitite is usually found in mountainous regions. To aid us in our search, we will be using core samples.
Core samples? What are those?
It's a way for geologists to analyze the history of the planet. They take a sample of the planet down to a certain depth.
Oh.
Excellent. Let's get going. Welcome. Let's see if we can be useful to the Empire. Please, load them into the sample analyzer.
So what are we looking for, boss?
Any sort of granitic rock. Scandium is bonded to yttrium and silicon dioxide, which is usually found in granite. If you find any of that stuff, please let me know.
I don't see anything we could use here.
Well, that's all right.
Nothing ever works the first time in science.
What's that white layer? It looks like it's in every core.
That's odd. That usually means something very interesting happened on the planet during this time period. It looks like it could be barium carbonate, but that makes no sense. This planet hardly has any barium on it.
Could it be something man-made?
There is something it could be. When humans first got their planet destroying nuclear weapons, they would test them on dead planets. These bombs usually used fission to power them. When uranium-236 decays, it breaks apart into barium and krypton and gives off 3 neutrons. Those 3 neutrons break apart other uranium molecules, and the bomb keeps going. It could be that the barium combined itself with the existing elements on the planet to form barium carbonate.
Boss, the computer's showing something else. It looks like there are fossils below that barium layer.
Impossible. Humans would never bomb a planet with life on it.
The rocks can't lie. He is right. The life looks really complex too. These are casts of organisms. There are 3 conditions necessary for fossils to exist. First, there needs to be enough hard parts for the fossil to survive, and there also needs to be enough sediment for the fossil to be preserved in the rock layer. Basically, what happens is that the organism dies but takes up space in the sediment layers. After it decays, another mineral will take its place and slowly rebuild that organism out of the new material.
That's really cool, boss. But how can fossils help us?
They can help us create what are called index fossils. Index fossils are fossils that help us determine how old a sediment layer was when it was deposited. If we know how old the fossil is, then we know how old the sediment was when it was deposited. Also, if we can find 2 distinct sediment layers with the same index fossils, we know that they have to have been deposited at the same time. Right now, our biologists are working on what we can use as an index fossil to help us determine when the sediment was deposited.
Boss, there's no life above the barrier. Not even a single organic particle.
There is supposed to be mass extinction on planets with life to help new species come about, but this is unheard of. Life simply seems to went extinct on the planet.
We must have our troops on high ground. They must be able to defend themselves.
I advise against that, sir. Taking high ground will bring fire.
Councilman, we have urgent news to deliver.
By all means, deliver it.
We have observed what seems to be a radiation boundary on the planet.
Radiation boundary, we've never touched the planet.
What's more, this planet once had life on it, but above the boundary, there isn't life.
Humans were never allowed to bomb a planet with life on it. No power would have done such a thing, whether the free world or the oppressed.
That's what we presume, sir.
But the fact remains that there is a radiation boundary on this planet. If it wasn't us, it was our enemies. This planet may have secrets that we need to divulge to help us win this war.
You have good reasoning, but what will you use the money for?
We hope to take more core samples to help us figure out the geologic history of the planet. If we can use the history books to figure out what this planet used to be in the past, we may be able to figure out what it is now.
Very well. You may have more money.
Thank you, sir. Oh, welcome. What took you so long? Chop, chop. Put the samples in. Let's get going.
Okay. But what exactly is the analyzer doing? How will this help us analyze the history of the planet?
Excellent question. When you look at the cross-section of the lithosphere of a planet, you'll find that erosion happens from the top down. Fluids start out at the tip of mountains and they go really fast, so they're able to carry all sorts of sediment, big and small. But as they go along the stream channel, they slow down and they drop off some of the bigger sediments. This is why we find big sediments near the mountainsides. But as they keep going, they're able to collect smaller and smaller sediments, which don't need as much energy to be carried. When you get to the beach, all the sand is deposited because there's no more energy for it to be carried. But the smallest sediment, the clays, are still entrained, and they keep going until the deep ocean. Until the deep ocean. At this point, they are also deposited. This is why we see clay in the deep ocean and sand in the beaches. If we can find sand surrounded by barium carbonate, we'll know what the beaches look like. And if we can find clay surrounded by barium carbonate, we'll know where the deep ocean was. Bam! We know what the planet looked like at the time of the explosion of the bomb.
Okay, I get how this works, but how's this going to help us?
If we find barium carbonate in a layer of sandstone, we will know where the beaches were when the event happened. If we find clays surrounded by barium carbonate, then we'll know where there was deep water when the event occurred. Then, using this data, we can reconstruct a map of the planet in the past. Bam! We know what the planet looked like when the event happened.
Looks like the screen's loaded. Can you take us through one of the core samples and show us the process?
Sure thing.
The trick to analyzing a core sample is to look at each sedimentary layer at a time and figuring out what they mean. The first layer at the bottom is bedrock, and usually does not tell us much about the lithography of the planet. The second layer here is clay, which is usually found in the deep ocean. So, wherever we see clay, we know that there must have been deep ocean there at some point in time. The next white layer is what we believe to be barium carbonate, leading us to think that there is a radiation boundary on the planet. The next layer is also clay, meaning the area was still deep ocean for some time after the radiation boundary. Finally, there is a layer of sandstone, which means that this area was a coastline. Because there are no more plate tectonics on the planet, this area is still a coastline, and none of the continents have moved.
Didn't you say something about plate tectonics earlier?
Yes, I did. Plate tectonics is the movement of a planet's crust. It can result in trenches, mountains, and all sorts of stuff. At divergent plate boundaries, magma or melted rock rises from the interior of a planet and pushes plates apart. At convergent plate boundaries, plates are ramming into each other. If there are two continental plates, they will make mountains. If one is an oceanic plate and the other is continental, then the oceanic plate will dive back into the crust, since it's denser than the continental plate. At transformed boundaries, plates are slipping past each other, causing frequent, strong earthquakes.
Does this planet have plate tectonics? Isn't it possible that the plates have moved since then?
Excellent point. But we have determined that the plate tectonics has stopped on this planet at around 4.5 billion years ago. We have determined that the youngest rocks are about 4 billion years old, and the oldest rocks are over 8 billion. So, after 4.5 billion years, there are no more plate tectonics on the planet and no new rock has been formed.
So how did you determine the age of a rock?
We use radiometric dating. We know that uranium-236 has a half-life of 700 million years. So, if I have a pound of uranium in 700 million years, I'll only have half a pound. In another 700 million years, I'll only have a quarter pound. So, by determining how much uranium-236 is on the planet, we can determine the absolute age of the rocks.
Your computer can do this all for us, right?
Yeah, we brought the GPS location from where all the samples from, so it should be able to. It's amazing what technology can do these days.
If only we're faster, right?
It's up.
That place seems familiar, but I can't put my finger on it.
Boss, you know what this is?
Yes, I do. Don't you? Council members.
Come in. We were told you had a breakthrough in this project.
We do.
There's far more history to this planet than we ever thought.
Is that so? What'd you find?
Through thorough analysis of our core samples, we were able to determine the exact history of this planet, and it's far more interesting than we could have ever pictured.
Well, this is amazing. We cannot let this happen ever again. We must call for peace.
Agreed. Hello, President Niput. We have something to show you.
President Niput, our scientists have recently made a discovery on one of the planets we've been exploring. We believe that this discovery will severely alter your opinion on the war.
We shall see.
Dr. Gladstone.
Good day, Mr. President. This is what the planet looks like in the current day. It has a carbon dioxide atmosphere, but no life on it. Our team of scientists were able to take core samples at different locations of the planet and determine which areas were above water and which areas were below water. We were then able to go back, reverse the plate tectonics 4 billion years and determine what the planet looked like in the past. Here's a map of what we think it looked like that many years ago.
This planet, it seems familiar.
Yes, it is. It is the birthplace of humanity, Earth. Our biologists were looking at interesting core samples when they realized they were fossils of primitive human beings. This is indeed our home, Earth.
Congratulations, you've discovered Earth. But why do I care?
5 billion years ago, planet Earth was habitable and thriving. This blue and green marble was populated with organisms of all kinds. Life was able to live in harmony for thousands of years, all up until the advent of nuclear weapons. But the demise of Earth did not directly follow the discovery of nuclear power. However, 600 years later, the supply of resources could not keep up with the demand. Our planet was overpopulated by the billions, and tensions finally rose to a breaking point. It was when technology had evolved to the point where we could produce explosions comparable to asteroid impacts did Earth's first and final nuclear war occur. It only took a week for all life on Earth to cease living. The second wave of nuclear weapons was already enough to eliminate life on Earth. But yet 19 waves of explosions rocked the Earth 5 billion years ago, destroying any possibility of life rebounding. The planet was left as a dangerous radioactive wasteland. Humans left in search of a new habitable planet, and Earth was forgotten to the ages, its memory dying as generations pass.
President Put,
President Zod.
we cannot keep going with this feud. We have managed to entrap the entirety of the human race in this war. This war for simple planet resources has taken too great a toll on the lives of our citizens and their loved ones. We must make peace, for I fear the annihilation of the human race.
What about all the madness, all the hatred, all the anger between us? You think that's just gonna go away? You think peace is gonna come easy?
No, I'm not saying peace will come easy. I'm saying it's the only option we have.
Alright. But I'm not making peace for you or for your fools. I'm doing it for the human race. And let history remember that.